All right, so we're going to start off with introduction to chance models. So really the key concepts in this section is going to be parameters versus statistics and really chance models. Like there are stuff about simulations, but you'll kind of get the hang of them as we go on. And we're really not going to simulate any coin tosses. Instead, we're going to use distributions, but you're going to see what I'm talking about as we go on with the video. So let's go on and go over a few key terms before we get into an example problem. Don't worry, I'm not going to bog you down with key terms and try and make you memorize something. I'm going to give you an example straight from the problem set, but not the same one from the problem set so that you're just repeating the same thing. I'm going to modify some words, change the context, and we're going to get after them and use the concepts to understand them. Not just throw words at you to kind of get you to memorize something that doesn't make sense. So, starting off with a parameter, I'm going to read it verbatim. A value that describes a population. Example, the proportion of cadets who received a top 3 branch preference. So that's the parameter. That's like the historical value. If you have a question, if it says historically or typically, that's probably your parameter. Now, a statistic is a value calculated from a sample which is used to estimate the parameter. Example, the proportion of 50 random selected cadets who received a top 3 branch preference. So in your question, when it asks you about a sample and gives you 20 out of 30, 30 out of 40, or whatever it gives you, that's going to be your statistic. What is the proportion on the given sample? Next, a chance model. This is just a way to model a random process like coin flips that helps us understand if observed data could happen by chance. So you could use like a distribution, or you could use like coin flips to kind of simulate it. Realistically, like think about flipping a coin. If you flipped a coin, you'd end up with something like a normal distribution if you went enough times. Now, if that doesn't make any sense, don't worry about it. You'll be fine. I'm not here to go through that. I'm here to get us winning and acing the test. So, the next thing is statistical significance, when the observed results are unlikely to have occurred just by random chance given a null hypothesis. What this means is, if let's say the historical percentage of cadets who get their top 3 branch break is 90%, and then your sample, it gives you 10 out of, or 5 out of 50 get their top 3 picks. So that's a pretty stark difference, and you kind of know that varies. I mean, we don't really need to do any math to say that 5 out of 50 is very far away from 90%. So what statistical significance means is, if we had a simulation where the statistic was 90%, where usually 90% of cadets get their preferred branch, is there a chance in that world of simulation that we get the off case with like through random chance that only 5 out of 50 get their top pick? And that's really what statistical significance is saying. Is that possible? Is 5 out of 50 due to a change in the way branching works? Has something changed? Or could it be due to random chance? That doesn't make sense. It's going to make sense later on. So let's start off with an example problem. So over here, I have an example problem, and we're going to use gym attendance instead of the branch night thing. So I'm going to read it out, and we're going to tackle it. All right, let's do it. Last year, it was reported that 80% of students regularly attended the gym at least 3 times per week. This year, you randomly survey 50 students and find that 35 of them attend the gym 3 times per week. You want to test if the proportion of students attending the gym this year is different from last year's proportion of 80%. So starting off, we're going to go with observational units. So what is an observational unit? Basically the things you are looking at. Not really what you're looking at, but the things. So in our case, we're looking at students. So they're going to be, the 50 student surveyed are going to be the observational units. So in the other one, it would be cadets or firsties branching. Nothing. Don't overthink this one. Now the parameter, remember the parameter would usually be typically associated with our historical proportion, and we use the symbol pi to say the parameters. So in this one, this is going to be the true proportion, which is given to us over here, or the historical data, 80%. So this is going to be 0.8. And then we have our statistic, which is in our sample, what was the proportion? And we got 35 over 50. And I'm going to quickly put it on my watch so I can Oh, wait, that's not that bad to do. It's 70%. Yeah, see? I know what I'm doing. Don't worry. I am not a random actor creating this video for you. I do know how this works. Just got stuck there for a second. So 0.7. So already you can kind of, if you look at it, you're like 0.7, 0.8. Are they far from each other? Could that have happened? That's what we're trying to do. We're trying to find the statistical significance. So we're trying to see factually, not or statistically, not like off our heads. We're trying to like get the concrete answer to see if it's actually statistically significant. All right, now we're going to go into the hypotheses. I just wrote it singular. I mean, we're going to have two. So we're going to have a null hypothesis, which I'll just go straight to. I'm assuming you guys know what it is, but really the null hypothesis means that our sample is not differing from the historical norm and that it did occur due to random chance. So let me read it and then I can kind of explain it better. So in this situation, the null hypothesis, which is given to us by H sub 0, that's a symbol, is the proportion of students attending the gym this year is the same as last year's. And you write that with symbols by doing pi equals 80. What this means is the proportion from our data, if we account for statistics, is going to be the same as the historical. So I understand our data set gave us 0.7, but what it's trying to say here is 0.7 could have occurred by random chance, so it's still valid to say that the historical or the general, the whatever's happening is equal to 0.80, and that statement isn't necessarily false. So again, I know our statistics said 0.7, but what we're trying to see here is if our null hypothesis is true, it still could mean that our sample gave us 70%, but 70% could have happened by random chance if we had a simulated world where 80% was the expected sample, the expected proportion, and we just simulated it 100 times. Because think about it. If you roll a dice 10 times, you expect to get 5 heads and 5 tails. But would it be unreasonable to get 6 heads and 4 tails or 7 heads and 3 tails? Not really. Those still could happen, even though there is a 50-50 chance. Now, if I said 9 heads and 1 tails, you'll be like, or 9 heads and 1 tail, you'd be like, okay, that's not happening. That can't be true. But 6 and 4 could happen. So that's what I'm trying to get with the null hypothesis. Like, does it seem reasonable to be 50-50? Now, the alternative hypothesis, H sub A, is going to be the proportion of students attending the gym this year is different from last year. So pi is not equal to 80. So in this type of problem, you really just need to see if it differs or it doesn't. And it should be pretty straightforward. So again, pi equals 80 or pi is not equal to 80. We're not checking if it's lower or above. We're just checking if it's different. So now we're going to do something called validity conditions. Now you might be wondering, why the heck do we need to do validity conditions? Basically, if it passes these things called validity conditions, I'll show you what it is later, we can perform something called the z-test, which allows us to use the normal distribution to do all our predicting. The normal distribution is that nice bell curve. Having it makes things a lot more fun, a lot more easy, so let's just go with it. So over here, we have the conditions, and now this might look like a bunch of jargon right here, and I'm going to quickly check my screen so I could do some fancy pointing. So let's start off with, what does n mean? N is our sample size. So in our case, it's 50 cadets or 50 students who go to the gym. Then P is the historical or the parameter. Remember I said before parameter was pi. Really it's the historical value. Can you guess it? 0.8. Yep, 0.8. And that's going to be great if the sample size times the parameter is greater than 10 and the sample size times 1 minus the parameter is greater than 10, we have validity conditions. Now, what does that mean? What it basically means is, if it's saying is that if we accept the parameter or the historical proportion to be true, and we multiplied it by our sample, would we have at least 10 in each group? So in our case, let's say the sample size is 50, and then the historical proportion is 0.8, so 0.8. And then we have 50 times 0.2. Does this all give us a value greater than 10? So this one would give us 10 over here. 10. And this one over here would give us, it would give us 40. Yeah, 40. Sorry. My bad. I'm trying to think on the fly while looking at it. So it's 40 and 10 right there. Let's go with that. So what it means is if we accepted the historical proportion to be true, we'd expect that we get 40 cadets who go to the gym and then 10 who don't. So it's greater than 10 for each, and that means we can use the z-test. If it's under, we can't use the z-test. Now, it's basically checking the data set size. You can throw in the word hint. If you get confused during the test, you might want to throw in central limit theorem. What it's saying is, as you add more, the more data you have, the better, the more you can use a normal distribution or a z-test to approximate. Really, the more data you have, the more approximation to a nicer curve you can do. That's what I'm trying to say here. And we're going to go down. Oh, so yeah, so we passed the z-test, right? 40 and 10, we have enough on each side. And now we're going to use the z-test. So before I do that, I'm just going to read this, what the z-test actually means. So the z-test is saying how far the sample proportion is from the hypothesized proportion measured in standard deviations. So the sample proportion in our case is 0.7. That's what we measured. Historical or hypothesized is 0.8. Now we're going to measure how far it is in standard deviations. That's all we're doing. So this is the formula. P hat minus P, and of course you don't know what that means because this is just a bunch of jargon. P hat is the observed proportion. Remember, we defined that above. Did we define that? Yep, P hat right there. It's the observed statistic. I say statistic and proportion. You can use them interchangeably. So that's going to be 0.7 minus the null hypothesis proportion, or the historical one, 0.8, and then over, we could just plug in our values over there. And in our case, if we do that, we plug them in, 0.7 minus 0.8, over the square root of 0.8 times 1 minus 0.8 over our sample size, and remember, n's the sample size of 50, we get around negative 1.77 is our z value. Let me write that a little nicer. Whatever you get here, even if you miscalculate it, just kind of use it. What it means is we're 1.77 standard deviations from the historical thing. So what we recorded is 1.77 standard deviations away. And then right over here, we have our final step before you can do your interpretation, which is, what is the p-value? They're going to ask you, how do you get the p-value? Now, you're going to need to use R to do this now. I'm not going to open up R in this. I'm going to assume you know how to use R. I can make a tutorial if you want on how to use R. But basically, to get it, we're going to perform something called a two-sided test. Now, two-sided test. Let me write two-sided test. Because sided test, like that sounds like some random thing that I'm just coming up with right now. Really what this means is we're trying to see, remember our original null hypothesis. We were trying to see if it's not equal to 80 or if it's equal to 80. We don't care if it's bigger than or less than. So really, if it doesn't care if it's bigger than or less than, and you just see the not equal sign or you come up with that, you're going to do a two-sided test. Just believe it and you'll be chilled. Like, you can read the course guide, ChatGPT, get you right, but I'm trying to get you winning here. So we're just going to believe it. So we're going to do, and I'm going to open up RStudio right now. And of course, I can jump cut if this takes too long. We got RStudio. So I'm going to do 2 times 1 minus p norm, the absolute value of z. So 2 times 1 minus p norm. I'm doing it on my computer, so you can't see it, but I'm doing this right here, this right here, this right here. So 2 times 1 minus p norm of the absolute value of z. And z was negative 1.77 absolute valued. And I get a p-value of 0.076. Cool. P-value. Don't get it confused with our other p's, like, you know, the historical or the parameter. Like, someone's going to get me for saying historical. Okay, now we just need to interpret it. So I don't mess you guys up. If the p-value is below 0.05, we have strong evidence to reject the null hypothesis. Really what it's saying is the chance of us getting 70% when the historical value is 80 is, if it's under 5%, yeah, that's because something's changed. Like cadets, the students have changed, the way they work out has changed, something has changed. But if it's over 5%, that's possible. Remember the coin flipping example. If I flip a coin, you might expect 4 heads and 6 tails. That's still reasonable. Same thing, if we get 50 students to work out and 80% of them are 3 days a week, it wouldn't be unreasonable to have 78% or 70% or 72% of them do it, just because that's how chance works. And in our case, we got 0.7076, which is like 7.6% really, and I just kicked my camera, and now it's messing up the green screen. Oh, we're good, we're live. So yeah, and this is the terms you want to use. We fail to reject the null hypothesis, meaning we can't say the null hypothesis is true, but we fail to reject it because we do think that it's still reasonable to say that the historical proportion is 0.8 because it could have happened by random chance. So that's problem 1. I know I went long through it, but we're going to breeze through the rest because now you're tracking what to do. And we're gonna knock it out, my friends. Let's do it. You got this. All right, so we're now going to move on to our second type of problem, which addresses using quantitative data. So it might look similar to the other problem on the surface through the words, but there's a slight difference that I'm going to go through and tell you what methods to use in order to get the question right. So to start off, I'm going to read out an example problem over here, and we'll get started. So the scenario is, a high school math teacher is concerned that her students may not be performing as well as the national average on the standardized math tests. The national average score on the standardized math test is 75%, or 75. She collects the test scores from 15 of her students to determine if the average score is less than the national average. To determine if their average score is less than the national average, The scores from her class are, and we got a bunch of data over here, so 15 scores to be exact. So teacher wants to see if her students are with the national average or under it. So starting off with the observational units, I've already written these down. This is going to be the students, or the students who are surveyed or picked by the teacher, however you want to phrase that. Now you might be tempted to say the test scores. You want to avoid doing that because you're really looking at the student, and the test score is a part of the student. So it's the student who's the observational unit. Now, quantitative or categorical. So this is going to be quantitative, and this is really where the magic happens with these types of problems. Quantitative means that your data is arranged, so like heights, weights, and in this case, it's scores. So qualitative would be that yes, no, 1, 0, preferences type thing. Quantitative uses numbers and a range of numbers, so that's what we're getting for this over here. Alright, so we have that set up, so we now know it is quantitative. Now over here we have another question. Based on variable classification, what type of test will you conduct to draw an inference about the population parameter? So we're going to use a one sample t-test. Let me explain this a bit. So it says based on your variable classification. So in our cases, if you see a quantitative problem, you're going to use a t-test. So rather than using the z-test like we used in the other one, we're going to use a t-test because it's quantitative. Now the reason we're using a one sample t-test is because we are finding out if the test scores are less than the average. So remember, for the other ones we were checking if it's different from the historical percentage or proportion. Right now we're just checking the less than side of the curve, so we want to do a one sample test. Okay, so what are the symbols and values of the observed statistics? So there are really two key things you have to have over here, and the main one is going to be X bar. So if you ever see this X bar symbol, let me X bar right over there, that's going to be our sample mean. What this really means is if we go up and we see our history or our test scores and we get the mean of that, so the mean of our sample, the sample mean, that's going to be X bar. So you're going to call that X bar, and that's going to be very crucial later on. Next, you get the standard deviation, which is going to be 3.94. you just calculate the standard deviation of all these numbers. And I'm going to show you how to do that in R later on, and even how to calculate X bar. So just take my word that they're these numbers for now. Remember, 71.2 is the standard mean, the mean of our data, and the standard deviation is 3.94. Now, moving on to our hypothesis. So the null hypothesis, or H0, is going to be the class's average score is equal to or greater than the national average of 75. And you can see we use this symbol over here called the mu. So remember how in the previous problem we used pi for the parameter or the historical proportion? Now we're going to use mu because it is quantitative. Really, use mu instead. Don't use pi for quantitative. And mu is mu is going to be mu is going to replace pi. Now you could also have an equal sign over here if you wanted. That would probably be a bit better. In our case, we're not really worrying about greater than. Like in our examples on our problem sets, we just dealt with equal to. So if you want to use equal to there, let's stick with equal to, because we either want to see if it's equal to the mean or if it is less than the mean. And really, that's why we're doing the one-sided test. So equal to or less than. Ignore the greater than. So we're not worrying about the greater than side. So the alternative hypothesis, I don't remember if I said it, is the class's average score is less than the national average. Mu is less than 75. So can we use theory-based methods? So on this data set, technically it might not pass the parameters, but typically a theory-based method can be used on a large data set because of the central limit theorem. So that's really going to be your lingo to answer the question. As the data set gets bigger, we can use the central limit theorem to approximate using theory-based methods. In this case, there are 15 observations, but I didn't want to have like 1,000 or 100 or even 30 for this example. So yeah, hopefully on the test they give you a big data set. All right, moving down, using theory-based method, conduct your hypothesis test, report the standardized statistic with the appropriate letters. So remember, we're going to be using the t-test over here. And as we saw before, because we have quantitative data, we're going to use the t-test over here. That's where I got it from. I didn't just make that up. So now it might seem that I have a lot of stuff pre-written. Don't worry, I'm going to go through it step by step. This is just the formula stuff and the lingo, so we're going to breeze through it. So the formula for the t-test is t equals x bar minus mu over s divided by the square root of n. Now that just sounded like numbers or symbols. Here's what they mean. So x bar again is the sample mean, the mean of the data we collected, the test scores we collected. Mu is going to be our parameter, so the historical average for test score, 75. S is going to be our standard deviation, 3.94. And n is going to be our sample size of 15. So you do that over there and you plug it in and you should get your answer for your t-values. So I'm going to do that with you guys real quick over here. So I'm going to enable my screen capture, make sure it's working, cool. And I'm going to open up Desmos. I have ChatGPT, just making sure I got everything right there. All right, so we're going to do our test. Now, the formula might not be displayed, but I'm going to quickly write it for you guys. So 71.2, which is our x bar, minus mu, which is going to be 75. And we're going to divide that by our standard deviation, which is 3.94. divided by the square root of n, which is going to be 15. So again, x bar minus mu over standard deviation divided by sample size. And we get negative, so I'm going to switch back to my iPad for you guys. We get negative 3.73. So 3.73, that's what we're going to get for that. And that's going to be our t-value. Okay. So let's continue on from there. Just making sure. Yep. And one thing to notice, that this would be called the standard error formula right here, this bottom part. So I'm just going to notice that standard error formula. So if it ever asks you for that, that's going to be your standard error formula. Now we're going to report the p-value from our test. Now the way we do this is using a function in R. So our p-value, be careful not to get confused between p hat, p. I know there's a lot of p's. So if you want to use different variables, up to you. I'm going to use p. So our p-value is going to be p equals pt, which is a function of our t-statistic and our degrees of freedom. I'm going to explain what that means. So let me just boot up R real quick. Check if it's working. Yep, it's working. So over here I have our score data. I just put it in a list over here. As you can see above, well, you can't really see above, but like you could use this read CSV. So just look at what you did on your tech lab or your problem set. In my case, I just manually put it in a list over here. Then to get the mean, all you do is do mean, and then you plug in your list of parameters. So mean, score data, standard deviation, score data. It gave it to me. So now to get the p-value, I'd do pt in the console down here. And then I do our t-statistic, which was negative 3.73. And then we have this thing called degrees of freedom. Don't get confused by it. It's just your sample size minus 1, n minus 1. So in our case, we have 15 samples, minus 1, 14. That's all it is. That's all it is. And as you can see over here, we got a super small p-value, meaning that, so our p-value is going to be, p-value is going to equal, let me go back to my iPad for you guys. Our p is equal to 0.001. So basically almost 0, so it's not really going to mean anything in our case. Let me just make sure I didn't typo that. So yeah, it looks about right to me. So if I typoed that, that's my fault. Let me just try one more time on my own. 7.73. And then 14. Yeah, basically not 1%. So we're pretty good on this guy. All right, so we have that ready. Now, what can you conclude about your hypothesis test based on the p-value, significance level of 5. So we are going to probably say that our null hypothesis is unlikely because it seems that our data could not have occurred by random chance, so it couldn't be that 75% just happened to give us a 70, let's see what it was, 71.2. And this is likely due to some factor affecting the students. That's what we can kind of assume. We can't really conclude anything, but we can say we are inclined to reject our null hypothesis, which is that it is equal. That it's equal to 75%, because our percentage is 0.01, or our percentage is under 1%. So something must be going up with these kids. So that's really what you can conclude about your hypothesis, that you can't accept the null one. All right, calculate and report the 95% confidence interval for your parameter of interest. This one's about to be really, really fun. So, to calculate the 95% confidence, what you have to do is follow this formula over here. X bar, just make sure you can see me. Sorry, I'm just getting paranoid. It's like 12:30 at night, and I don't want to re-record this as much as I love statistics. S over square root of n. Now, don't worry, I'm going to explain what everything means, but basically, you have your x bar, which is your sample mean, and then you have your t star, which is going to be something we calculate later using our we're going to calculate it later. And then we're going to multiply that by the standard deviation over our sample size, square rooted, of course. So we're going to first, before we do this, we need to find what this t star is. So let's find t star. Find t star. And the formula, it really is just going to be t star equals QT 0.975, and then we're going to put in our degrees of freedom. So, degrees freedom. Now remember, I'm not going to bore you or try to confuse you with lingo and what I did. So, let's explain this. So, the 14 we got from our sample size minus 1. So, 15 minus 1 is going to be our sample size. So that's our degrees of freedom. So that's good. Now we're going to move on to this 0.975. You might be wondering, where did you get that when you were talking about 5%? Really, the key is to subtract half of your percent. So we had 5%, we're subtracting 2.5%. Sorry, that took me a second. Sorry, wait, that was not right. We had 5%. We are subtracting 2.5. Yeah, 2.5. Yeah, we're subtracting 2.5 from each side. Sorry, that makes sense now. 97.5% plus 2. Yeah, so we're subtracting 2.5 from each side because of the 5%, and that's going to give us 0.975. So I just spent like 30 extra seconds on that when I didn't need to. That's okay. So that's how we're going to do it. And then we're just going to plug this into R to get our value. So I'm going to re-enable R for you. And you can see that over here at the bottom, right where my mouse is in super small. Hopefully you can see it right here. I'm going to do QT 0.975. 14, which is our degrees of freedom, and I get T star is equal to 2.14. So 2.14, and then from there we can continue on with our thing. So 2.14, now we can simply plug it into the formula in order to get our 95% confidence. So it'd be X bar. So in our case, X bar was, we gotta find X bar, 71.2. So we're gonna do 71.2 plus or minus 2.14, and then we're gonna do times our standard deviation. So we can go up to find our standard deviation, 3.94. So it's gonna be 3.94 over the square root of our sample size, which is going to be 15. And there we go. That should be it. Let me just quickly look at it. Yep. And that is going to be our thing. So the way we write this as a confidence interval, since it's plus or minus, would be you just plug all of this into Desmos with the minus sign. So I'm just going to be kind of lazy over here. Or I could do it for you in Desmos. You know what? I'll do it for you. That's my guide over there. Just make sure you guys can see my screen. Cool. So what I'm going to do is I'm going to do 71.2 minus 2.14 times 3.94 divided by SQRT 15. So 71.2 minus 2.14 times 3.93 over the square root of 15. That's what I got from the formula. And then I'm also going to do this exact thing, but with plus, because remember it's a plus or minus, and I get two values, and I can now make my range. So we're going to re-enable our iPad screen, and it's going to be, sorry, I'm losing it on my screen, 69, and I'm not going to put the decimals to 73. Put your decimals. Don't be lazy like me. Again, 12:53 a.m. Things are going to die. My phone's about to die that's recording this. So that's good. That's our confidence interval. Is there anything else? No. So that's really the general gist. This is your confidence interval. Again, I just want to highlight what it is. So what the confidence interval means is we can be 95% certain that our students' test scores lie between 69 and 73, but we do know also that they are not equal to what the historical value was or what the parameter was that was given as 75. So it does differ from the null hypothesis. I'm not going to go as strong as saying reject. Ask your teacher if you can say reject. But what I'm going to say is our null hypothesis is probably not probable. Probably not probable. And that we are 95% sure that the scores are between 69 and 73. So with our accuracy, we can kind of predict that. So that's question 2. Remember, t-test for quantitative. Remember how to do the t-test, and you should be good to go. Run over your problem sets. Again, this video is probably just a test. If you happen to watch this video before the WPR2 or the T, good luck. Maybe the information in this is solid. Otherwise, it's probably going to go through a little bit of a tweaking process. But whatever, good luck. Have a great night, have a great day, have a great week, have a good T, have a good WPR, have a good quiz, have a good problem set. Kadesh Sharif, out.